In this session, we will continue solving problems on pericyclic reactions. The first reaction here is in the following sequence of pericyclic reactions X and Y, or we need to find the intermediate X and the conditions Y to get the final product. And this is the starting material, and these are the set of rules we will follow for doing electrocyclic ring opening and ring closing reactions. And first, we should be able to find the number of pi electrons present in the given substrate or a given conjugated system. Here we have 8 electrons. It would become an example of a 4n system. And a 4n system under photochemical conditions is this rotation is allowed, but we cannot do this rotation here by looking into the orientation of the substituents in the final product, as these two are trans to each other. When this is closed in a disrotation fashion, these two will become cis to each other, so that is not required. So we will not follow this condition what is allowed here. We would follow the 4n. A photochemical conrotation is followed. When you do photochemical conrotation, you will end up getting this product here. This is the conrotation symbol shown here. These are the arrows which are marked in blue will represent the conrotation. Then the electron reorganization would give you this product, and this under again thermal conditions. Here now we have a 6 pi electrons. This would become an example of 4n plus 2 system. If you give n is equal to 1, it will become 6. Under thermal conditions, it gives this rotation, and as in the product also, these two hydrogens are cis to each other. Cis to each other. We will close this ring by doing this rotation. 4m plus 2 thermal this rotation. Then this is X. This would become Y. So this is the answer. The X is this, and Y is thermal condition this rotation. And the next problem here is the following transformation involves. So here the give two reactants are given under acidic conditions. This is the final product. It would undergo a series of reactions to give you the final product. And the first step is the condensation of the aldehyde carbonyl group with the secondary amine to give iminium ion. This iminium ion would become a suitable substrate for doing same thing is written like this, for doing 3,3 sigmatrophic rearrangement reaction. For doing 3,3 sigmatrophic rearrangement reaction, you need to give the terminal sp2 carbons 3, 3, 2, 1. This takes 3, 2, 1. Then 3, 2, 1. Break the bond between the carbons 1 and 1 and break the bond between the carbons numbered 1 and 1. You do that, then you will get this product, and this would become the suitable substrate for doing managed reaction. Managed reaction is addition of a carbon ion to a iminium cation. So this lone pair of electrons present on oxygen would come onto this bond, double bond, makes a double bond, and this pi electrons through this carbon make bond with this carbon, and this pi electrons will go on to nitrogen and make it neutral and gives this final product. So the series of reactions that one should follow to get this product from these two substrates is an iminium ion, a 3,3 sigmatrophic rearrangement reaction, and managed reaction. And with respect to the following biogenetic conversion of furismic acid A to 4-hydroxyphenyl pyruvic acid, the correct statement is, this is the given substrate. With this substrate, what we can do is, we can do Claisen rearrangement. This Claisen rearrangement is the 3,3 sigmatrophic rearrangement involving the system of allyl and vinyl ether. This is the vinyl group, this is the allyl group. Do 3,3 sigmatrophic rearrangement reaction, then you will get this. Then this would undergo decarboxylation followed by oxidation, will give the final product. So the answer for this is the Claisen rearrangement and oxidative decarboxylation will convert B to C. The major product formed in the following concentrated reaction. This is the given conjugated substrate given here. So this contains 6 pi electrons, 6 electron system. A 6 electron system is an example of a 4n plus 2 system. If you give make n is equal to 1, it becomes 6 under thermal. This symbol represents the thermal conditions. Under thermal, we must close this conjugated system in a disrotation fashion. For closing the conjugated system in a disrotation fashion, we need to have both the substituent present at the terminal sp2 carbons. These two are the terminal sp2 carbons. This is one substituent. The other substituent is not given here. So we should write the other substituent, the hydrogen, like this. We cannot write the hydrogen substituent inside the conjugated system because sp2 carbons around sp2 carbons, the angle between each bond must be approximately 120 degrees. So we should write the hydrogen outside of the conjugated system here also. Then this set of rotation shown here will become the disrotation. So one is doing anti-clockwise, the other doing clockwise rotations. When we have the rotations like this, they will become disrotation. Then if you do like this substrate will go up, and when you rotate like this hydrogen also will go up to give you this product. The answer for this question is option A. And in this following conversion, the two-step conversion of cyan dihydroxy cholesterol to this product, what are the series of reactions it would go and go. First, we should need to break the open this six-membered cyclohexadiene system. While opening the cyclohexadiene system, we must open such that the substituents here, methyl and hydrogen, should go outside of the ring system, and the substituents which are part of the ring system, part of the other ring systems, will be inside the ring system. So we should now open this ring by doing either a conrotation or disrotation, so that which one would give the substituents outside of this conjugate system. So this methyl should come right, and this hydrogen should come left. Then only it is possible to. Otherwise, it would become a geometrically constrained system. So we should open the cyclohexadiene system so as to get the methyl and this methyl group and hydrogen outside of the system, outside of the ring system. So for that, now this is a example of a ring opening reactions. In addition to the 5 electrons, we need to take 2 sigma electrons also. So 2 sigma electrons here, and 2 pi electrons, total 6 electrons. A 4n plus 2 system, when you do under photochemical conditions, the 4n plus 2 photochemical conrotation is allowed. Then if you do conrotation, if you open the ring in a conrotation fashion, then this methyl will come here and this hydrogen will come here. Though hydrogen is not shown here, the hydrogen is here. Both the substituents, methyl and hydrogen, are outside of the conjugated system. Then it would become possible to do now the 1,7 sigma-trophic thermal reaction. Though interfacial is not favored, so in case of a large ring systems like 1,7 sigma-trophic, 1,7 thermal interfacials also will become geometrically feasible. For doing 1,7 sigma-trophic rearrangement reaction, there must be a conjugated triene system. Then, so this methyl group that has come, I just have taken one hydrogen out of this methyl. This is now CH2H. Now, number the hydrogen which would migrate. So this hydrogen takes the number 1, and the carbon to which it is attached will also take 1. This is 1. Then this also is 1. 1, 2, 3, 4, 5, 6, 7. Then this carbon would abstract this hydrogen, and this bond electrons will come onto this, and this pi electrons will come here, make it double bond, and this would go here, and these electrons have already abstracted this hydrogen to give you this product. So to get that product, one should do this photochemical, electrocyclic, conrotatory ring opening, and thermal interfacial 1,7 hydrogen shift. The option B. And the major product when formed when 3R4S 3,4-dimethyl hexa 1,5-diene is heated at 240 degree is. First we need to write this molecule like this. This is the stereo chemistry of this carbon and this carbon. This takes 3R and this takes 4S, and you all know how to do this in the configuration of a chiral carbon. The highest priority group here is sp2 carbon takes 1, then this carbon takes 1 because it is substituted, then this carbon takes 3. So if you go from here to here, 1, 2, 3, and also the lowest priority group, hydrogen, which is away from the viewer, so it is now clockwise. So this takes R, and now this carbon is configuration is given as 4s, because if you give numbering to the substituents around this carbon, this takes 1, this takes 2, and this takes 3. So we are now going from 1, 2, 3 clockwise direction, and also the least priority group is towards the viewer. So a 4R must be taken as 4s, because the least priority group is towards the viewer. So we will just invert the configuration to 4s. So also 4s, and when you bring the reacting sp2 carbons to a close proximity, then I need to rotate one of the this bond about 180 degrees, so that the methyl which are below here, it come below. To come from here to here, you just have to rotate 180 degree. Then the one of the methyls would change its position, which is below would come above. Then take this compound and write in the form of a 6-member chair form. And while writing that, we need to maintain the uh, geometry of these two methyl groups, as these two are cis to each other, and here also they are taken as cis to each other. This is axially up, this is equatorially up, and now this would become a good substrate for doing 3,3 sigma trophic rearrangement reaction. Do 3,3 sigma trophic rearrangement reaction, make the bond between the carbons number 3 and 3, and break the bond between the carbons numbered 1 and 1, and followed by the pi electron rearrangement, we would end up getting this product. So this product is a octadiene system. In case of octadiene system, the one of the double bond is cis, the other double bond is trans. So we end up getting an octadiene system with one double bond trans and with one double bond cis. So the answer for this, if you start numbering from here, 1, 2, 3, 4, 5, 6, 6, 2E, 6Z, octa, 2, 6 diene. That's all is about the answers for these questions.